So in today's lesson, we're going to discuss two main types of mechanical waves and what their properties are. So the two types of waves we're going to be discussing are transverse waves and longitudinal waves. Now remember that a wave is simply a transfer of energy through a medium, and that's caused by vibration. So now we're going to examine, well, how can energy be transferred through a medium to produce a wave? And what different ways can that happen? So let's talk about a transverse wave first. So a transverse wave is, you can see one here, and notice this person who's creating a pulse to start this wave is creating a disturbance. The wave is actually moving in this direction, but the motion is up and down. So one thing that characterizes a transverse wave is that the particles in the medium, are vibrating at a right angle or perpendicular to the direction of the actual wave motion. Let's look at this in an animation. So there are a couple of things that I really want you to pay attention to here. Of course, the transverse wave, you can imagine if you had if you were holding a slinky and kind of creating a pulse to make that slinky go, that it would create this sort of a wave. It's called a transverse wave. But pay close attention to the red dot here. Now notice that we tend to think of a wave as moving from one end to the other. However, it's the energy that is moving, not the particles themselves. Let me try to draw a line here and show you what I mean. So now this is stopped. But I'm going to see if I can do this and get this going again. So let me see. Here we go. Well, folks, it's not going to let me do it, but that's okay. What I want to do is just maybe if you can, just try to focus your attention on that red dot. Notice that red dot doesn't move to the end of this wave as the energy does. So a good example that I like to use of a transverse wave that you would see in your everyday life would be if, let's say, you were plucking a guitar string. Now you're plucking the guitar string perpendicular to the way that that wave would be created in the guitar string itself. Some people will often use water waves as an example, and water waves are, generally speaking, primarily transverse waves, but we'll look at that a little bit more in a little bit more detail later on. So the second type of wave I want to discuss today is a longitudinal wave. So in this type of wave, the particles, instead of vibrating perpendicular to the way that the wave is being transmitted or the wave is moving, it is parallel. So this is a little bit harder for you to see, but imagine that you were holding a spring at one end and you were just giving it little pulses forward. You would create these areas of compression where the spring would be a little bit closer together, and you would see these areas where the spring is a little bit more spread out, and that has a name. It's called a rarefaction. So again, the wave would be moving in this direction, and the pulse would be parallel to that direction of the wave. So let's take a look at this in an animation as well. There are a few details here to pay attention to. Notice that the wave, the energy is moving through this particular medium, but notice the particles themselves are just sort of moving back and forth. They're not traveling along with the energy. They're sort of mostly staying in the same spot. Okay, so the particle itself is moving back and forth. You can see here areas where it's more compressed and areas where it's a little bit more relaxed. So you can see those compressions versus the rarefactions as the wave is traveling. So here are a couple of definitions for you to write down for what a compression is and a rarefaction. So take a minute to do that if you feel that you need to add that to your notes. Well, people will say, well, what is an example of a longitudinal wave that we might see in our everyday lives? Well, sound is a great example of that. I've mentioned sound before in our previous screencast. So sound waves will travel, and as you speak, particles of air get compressed in certain areas and are rarefacted in other areas, and that's our sound wave traveling from one person's mouth, the sound coming from their mouth, to the person who is hearing them's ear. So let's take a look at these two types of waves side by side, right? So I think this really demonstrates the difference. Here in the transverse wave, we see the pulse is being transmitted perpendicular to the direction of the wave, whereas in the longitudinal, we can see as the pulse moves through, there's an area of compression. There are areas of rarefaction where it's less compressed. So I mentioned that I would talk about water waves a little bit later on in the screencast. Water waves are an example of what can be considered a complex wave motion. So it's not like it's a black and white situation, one or the other. Sometimes we have combinations of longitudinal and transverse waves existing in the same scenario. So when you can see this water wave here, now the water waves near the top, remember there's the wind that is blowing to create these water waves. And so the water waves are going to experience a longitudinal wave action near the surface of the water in combination with the transverse wave that's already occurring. And so the wind at the surface is going to have an effect, whereas it's not going to have as drastic an effect as you move lower and lower to lower and lower depths within the water. So notice that in a water wave at the surface, you have sort of almost like an oval or circular type motions the water will experience. And that's again due to the combination of our transverse wave and our longitudinal wave caused by the wind action. As we move down to a lower depth, we see that that circle gets smaller just because the wind doesn't affect particles that are lower beneath the surface as much as those on the surface itself. And of course, as we move to lower and lower depths, the longitudinal aspect of the wave becomes almost negligible. So in case you were wanting to add a little bit of that to your note, again, here it is in writing. Wind pushes water at the surface forward, producing a longitudinal wave in addition to the wave's transverse motion. So this is an example of a complex wave that I found from your textbook, and I thought it was useful, so I thought it made sense to mention it. So here we have a hammer that's hitting some sort of a surface, possibly, yeah, not really sure. There's no nail here, but, maybe we can imagine a nail. You can imagine that if that hammer were hitting the surface, then, the motion is perpendicular to how the wave's going to be experienced, because that wave is going to kind of create a vibration in the handle of that hammer, and you're certainly going to feel it. So, but by the same token, right? And so you're going to also feel that in the wood beneath. But also, we're going to see that there'll be some longitudinal waves created once that initial hammering happens, because it'll vibrate sort of parallel to the motion of the hammer, right? So you're going to feel that wave coming down, and that would make it parallel to the direction of the motion. So that's it for our short discussion on the types of mechanical waves that we're going to be discussing in class. Be sure to reserve any questions that you have, and I'll be happy to answer them for you.